Hello everybody, my name is Matt Whiting, and today we're going to be talking about the Doppler shift, or also known as the Doppler effect. Most of us have probably already learned about the Doppler effect and how it is involved in everyday life. We probably all heard it as well as sirens past us, but if you haven't heard it or if you don't remember what it is, I made some videos to kind of help you remember what I'm talking about today. The first one is just if you're in the car's horn is honking, and we're not changing our position, we're just going along with the car. So here's that sound. So you probably noticed the frequency of the horn didn't change because we were moving with it. So what if I was an observer on the side of the road and I was listening to the car as well as it moved past me as I was honking its horn? So here is that video, and we can listen to that. So I am a stationary person and the car honking its horn is moving towards me and then it moves past me, and I hope you could hear that little change in frequency as the car went past me, but we can listen to that again and listen to the subtle change as the car passes me as it's honking its horn. So in essence, that little frequency of the horn changing from a higher pitch to a lower pitch is the Doppler effect. There is a really good definition from Sheldon Cooper from the Big Bang Theory, and it says, "It is the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer." There was a episode of Big Bang Theory that he dressed up as the Doppler effect, and I'll put a link to the video so you can watch it. It's pretty funny. But here is his costume of the Doppler effect, so you can see how the lines are really close together in the middle, and then they get farther apart as they go towards the sides and the edges. And here's a little animation of a car honking its horn as it's passing a bystander on the sidewalk. This person could be moving or not moving, but here we go. You can notice that the rings kind of get bunched up to the right of the car, and they kind of get more spread apart on the left side of the car. So the more bunched up is that high pitch frequency that we usually hear as the car is coming towards us. And then those spreading apart of the waves is the car going away from us. And that is the difference. So you can kind of tell from this animation that the waves kind of get more pushed together and higher, and then they kind of get longer as the car is going away from us. So there is an equation to figure this out, and this equation that I have right here is just for stationary people. So if the observer was stationary, then this is what the equation would be like. So we have the frequency of the observer equals the frequency of the source times the velocity of the speed of sound, or c, over the velocity of the speed of sound, plus or minus the speed of the source. So that plus or minus is very key because if it's minus sign, we use it if the object is coming towards the observer, and then we use the plus sign if the motion is away from the observer. So there is a great example for just a stationary person as a train comes by in our OpenStax College physics textbook that we've all been reading this semester. So it says, suppose a train that has 150 hertz horn is moving at 35 meters per second in still air on a day when the speed of sound is 340 meters per second. What frequencies are observed by a stationary person at the side of the tracks as the train approaches and after it passes? So there's that equation again, and we'll use it into this as we use those numbers for the speed of sound, the speed of the train, and the frequency. So remember, if it's coming towards us, we use the minus sign. So our equation will look like that. So the frequency of the source is 150 hertz, and then the speed of sound is 340 meters per second, and then the train is coming towards us, or the person on the side of the tracks, at 35 meters per second. So we're going to use that minus sign. So if we add all that and times them together, we get 167 hertz. So remember if it's going away from us, so now we need to find out what the frequency of the horn is as it's moving away from us. So we use that same equation, but we have the plus sign instead in the denominator. And same numbers, just changing that minus sign to a plus sign, and then times it all together, and we get 136 hertz. So this shows us that we can mathematically figure out the difference. So we found that the train, as it's blowing its horn, is coming at a frequency of 167 hertz. And then as it's going away from us is 136 hertz. So we can show physically that there is a difference in what we are hearing. So it's not just some magical thing that is happening to our ears, but it is mathematically proven that there is a difference in the frequency. So I thought this was really cool. I think the Doppler effect is really cool, but also works with light. I didn't understand this until this semester when I was working on this project, but I thought it was super cool, obviously. So light acts like a wave, just like sound does. And we've learned that in our classes. And so it's coming towards us. The light will have a shorter wavelength because it's getting closer and closer together, the wavelengths are. So it'll have what's called a blue shift. So we know the blue wavelength has a higher frequency, a shorter wavelength. And if it's going away from us, it'll have a longer wavelength and a lower frequency. And we know that will be a red shift. Unfortunately, we can't see it with the naked eye. There are only certain ways we can measure it with what is called a spectroscope. Unfortunately, I don't have one, so I'm not able to show you what the light looks like, but those are the wavelengths, and you can definitely tell that the blue has a higher frequency and a shorter wavelength than the red does. So we can tell, and this is how scientists can tell that we are moving away from the galaxy or started moving away from us or towards us by what light it's giving off. And I thought that was super cool as it does that. And if you want, there's also this equation. It's the same concept as the sound. So we have lambda, or the wavelength of the observer, equals the wavelength of the source. And then that's the square root of 1 plus u is the relative velocity of the source to the observer, and then c is the speed of sound, or speed of light. And so we can figure out what the difference is in the equation between the light, if it's moving away from us or if it's moving towards us. And I also thought this was really cool. The Doppler effect, we can use it for boats, and the speed of supersonic boom from planes. And if you ever heard that, it's really cool. And it's also used in ultrasounds to monitor fetal heartbeat, measure blood velocity, and detect occlusions or blockages in the heart. So I thought those were all really cool. I think the Doppler effect is an awesome thing to study. It's in our everyday lives. And thank you for watching. Hope you have a great day.